Hello there. This is a video session on what is Gray code. Gray code is a code named after the American physicist and researcher Frank Gray, who worked at the Bell Laboratories. This is a non-weighted code. That means the position of the bits do not carry any weight. So for example, we are familiar with, let us say, the binary number. Let us take a binary number, say 1, 1, 0. Now we know that in this binary number, every bit has an associated weight. So if we start with the least significant bit, this has a weight of 1, this has a weight of 2, and the next bit has a weight of 4. So as far as the binary number is concerned, we say it is a weighted code. But a Gray code is a non-weighted code. That means the position of the bit does not carry any weight. This is one of the most important properties of the Gray code. That means the successive code words or the successive codes differ in only one bit. We will see how this becomes very useful. This is also called as a minimum change code or the unit distance code or a minimum error code. So it is also called as a minimum change code because as we go from one code word to the next, there's a change of only one bit. It is also called a cyclic code because the words are differing by one bit position only. As we go from one word to the next, there's a difference of only one bit. This code is a self-reflecting code. This is again an important property which we will see how it works out, how we can use it to generate the complete Gray code. Where will this code be used? This code is useful in A to D converters or analog to digital converters, and it is also used for error detection and correction in transmission of digital signals. And of course, we'll be studying Karnaugh maps in one of the sections, and at that time we will see that Gray code is extremely useful. And since there's a change of only one bit, the switching operations are reduced and it becomes a power efficient code. And last but not least, this is a very important property. This code is not suitable. It is not suitable for arithmetic operations. Right? Okay. Now let us take up these properties one by one and see how they apply to this particular Gray code. Here we have the decimal numbers from 0, 1, 2, 3 up to 15. We have their equivalent binary values in 4-bit 0, 0, 0, 0, and coming to 15 we have 1, 1, 1, 1. Now the Gray code is shown here. We will see how to generate this Gray code, but let us study a few properties of this Gray code and compare it with the binary code. First, we saw that Gray code is a non-weighted code. That means the position of the bits do not carry any significance or any weight. There is a difference of one bit in successive codes, or it's a minimum change code. Now let us understand what this particular point means, and to understand this we'll use the example from this table. The decimal value of 3 is 0011. As we go from decimal 3 to decimal 4, the binary value of 4 is 0100. Now you can observe as we go from 3 to 4 equivalent decimal values, there is a change of 3 bits. For example, the bit 1 has changed to a 0. This next bit 1 has also changed to a 0, and this 0 has changed into a 1. So as we just move from one decimal digit to the very next decimal digit, the 3 bits of the binary number out of the 4, 3 bits have been modified. But let us compare that with what happens in the case of a Gray code. So for decimal 3, the equivalent Gray code is 0010, and for 4 the decimal code is the equivalent gray code is 0110. And you can observe as we go from 3 to 4, the gray code, the 0 bit remains the same, the 1 bit remains the same. This 0 bit has changed to a 1, but the next 0 bit remains the same. So if you compare these two gray codes which are of successive values, then there is a change of only 1 bit, and therefore we say it's a minimum change code. But here, when you compare it for binary, the change in bits was as much as 3 bits changing at the same time. But let us observe that self-reflection feature here. Let us consider the first gray code 0000 and the last gray code which is for decimal number 15. Observe that the last three digits of this are 000. The last three digits of this are 000, and the difference in the two codes is only in the most significant bit. Here the most significant bit is a 0, and for this the most significant bit is 1. Look at the next one. The next gray code is 0001, and if you compare it to this, it is 1001. Again, observe these three bits and the last three bits here, they are the same, and all that is changing is the most significant bit has changed from 0 to 1. Let us take the next one, 0011, and the third number from the bottom, it has the gray code 1011. Again you can see that 3 bits here and the 3 bits in this, they are the same, and only the most significant bit has changed from a 0 to a 1. And this pattern, in fact, you can observe it as we go to the next pair of bits or the next one, and observe it here. Again in this case, the last three bits 101, the last three bits 101, and where do the bit patterns differ? Only in the most significant bit. A 0 has changed to 1, and we can observe that here. So this becomes a self-reflecting code. Now, supposing we have a gray code representation of n bits. This n may be, for example, 4 bits. To obtain the gray code representation for a larger number of bits, say n plus 1 bits, we will write down the two n-bit representations one below the other. We'll see this in the example, and we will append a 0 at the beginning of every code in the first group, and we'll append a 1 at the beginning of every code in the second group, right? And the least significant bits we'll have here. Now let us start this example. In this, we have a 3-bit code that is being generated in the last column. But let us start from the beginning. We start with the 2 bits 0 and 1. These 2 bits, we can see they differ in only 1 bit, and therefore we can say this is the simplest gray code that we can generate, which is out of 1 bit. Now, how do I extend this to a 2-bit gray code? So what we'll do is we'll first take the original bit 0 and 1. These are our original bits 0 and 1. We'll create a mirror image of this pattern, so 0 and 1. So you can imagine that there is a mirror here, and we have now generated the mirror image 1 and 0. So this one, its mirror image is 1 here. This 0, its mirror image is 0. Now what we do is we take these 4-bit patterns. So we have 0 1 1 0. This is 0 1 1 0. In front of the pattern which was in front of the mirror, so we have 0 1, we'll append a 0. So 0 0. So this 0 0 gets appended to the part which is in front of the mirror as if, and coming to the part which is the reflection, the mirror reflection or the mirror image, the 1 and the 0, these are the ones and the zeros that we got, we append this with 1 1, and therefore our gray code becomes 0 0 0 1. You can see there's a difference of only one bit is changing. As we move from here to the next, 0 1 1 1, again this one bit remains the same, but the 0 has changed to a 1. Again 1 1 1 0, we can observe the 1 has changed to a 0, but this one bit remains the same. Now we create a mirror image of this so that we can have a 3-bit gray code. So how do we do that? We take these 4 bits and we write these 4 bits here: 0 0 0 1 1 1 and 1 0. Again we create a mirror image of this. So 1 0, this 1 1 becomes a mirror image here, 0 1 becomes a mirror image here, and the 0 0 becomes the mirror image. Again, the part which is ahead of the mirror or the part which is in front of the mirror, we append a 0 before that. So again, let us visualize. Here is the mirror, we append a 0 in front, so this become our bit patterns for the gray code. And the part which is let us say the reflection of the mirror image, we put a 1, and that becomes our gray code in 3 bits.